Hello everybody. Today we have a lesson on physical and chemical changes alongside physical and chemical properties of matter. Some of this material is going to be review from previous science classes, right? This isn't necessarily brand new material, but we are going to focus on a couple of things that might be new, so we're going to do it up. First, we're going to look at the idea of a physical versus a chemical property. Right? If I have a substance, right? Let's say I have this rock. Right? This rock has a bunch of different properties, both physical and chemical, and if I want to begin observing this rock and taking measurements on this rock and finding out more information on this rock, I'm going to get two different types of measurements, two different types of properties, physical and chemical. Physical properties are the things that you can observe without changing the substance, right? So I see this rock and I say, this is a white rock with a red outline. That's a physical property of the rock. The color of the rock is a physical property. It doesn't change and become a green rock once I make that measurement. It doesn't change and become a bird when I make that measurement, right? This rock, the taking of the measuring of the color of this rock is not going to change the rock. Same thing goes for weight and length and width and height and density. All these things that you can measure without taking this rock and making it something else, without changing the properties of this rock, the substance inside. A chemical property is a property that you can only observe if you are going to change the substance. So for example, if I wanted to see if this rock reacted with acid, and I poured acid on the rock, that would then, if it reacted, change the properties of the rock. It would make something else. There would be a chemical reaction that happened, a chemical change that happened. If I wanted to see what happened when I put this rock into a really hot environment and I put it into a fire, and that rock started reacting and changing because of the fire, that would be a chemical change. Right? The key difference between the idea of a physical property and a chemical property is the idea that one, physical, does not change the identity of the substance, but a chemical property, measuring that property, observing that property, changes that substance into something else. And so immediately connected back to that, right, is the idea. Don't get out of there, you. Right, immediately connected back to that is the idea of a physical change versus a chemical change. A physical change is a change to a substance that does not change the identity of the substance. Whereas a chemical change is a change that does change the identity of the substance. You end up with a new thing at the end. So the two examples I have up here are the idea of tearing paper in half and the idea of burning a piece of paper. Tearing a piece of paper in half is a physical change. You have changed the paper, right? You've changed the dimensions of the paper, but you haven't changed the identity. You didn't tear it in half and end up with 2 slices of cake. Right? You didn't tear the piece of paper in half and end up with something else. You have paper still. Whereas with the burning of the paper, you end up with a different substance at the end, right? You started with paper, you lit it on fire, and now you have ash. And ash is not the same thing as paper. I can't take my ashes and spread them out in an 8.5 by 11 rectangle and then start taking notes on them. Right? That's not the way that's gonna go. Right? So a chemical change, I'm gonna finish these words. Chemical change changes the identity of the substance. You end up with something new or multiple new things. A physical change does not change the identity of the substance. You still have the same substance that you started with. And so with that, we're going to do a couple of practice problems. Pouring water on the paper is a physical change. You end up with wet paper, but you actually haven't chemically altered the paper at all, right? You cause the ink to run a little bit, but eventually the water is going to evaporate out of the piece of paper and you're going to end up with your piece of paper back again. It'll be crinkled and like kind of messy because those not once really straight lines are now going to be like warped because of the water that you poured on it. But it's still a physical change. You don't have something new. You have water and paper, and you put them together and you got wet paper. Right, so it doesn't actually change the identity of the substances. Right. On that vein, let's look at some more or less everyday examples. Right. Melting a piece of ice. Is that going to be a physical change or a chemical change? Right. So, melting a piece of ice is actually a physical change. You started with water, right? You started with a block of ice, and you ended up with a puddle of water, but it started as H2O, and it ended as H2O. You did not change the identity of the substance. This ice cube didn't melt and become something different. It went from the solid form to the liquid form of water, but it didn't actually become a new substance. Right. What about lighting the burner on your gas stove? Right? Chick, 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 chick. Now you've got some fire coming out of your stove. The change happening to that gas, is that a physical change or a chemical change happening to the gas coming out of the stove? So this one's a little bit tougher, but it is a chemical change. All right, good. Combustion is chemical, right? When you have a substance and you are burning that substance, you are ending up with a new thing at the end, right? Just like we burned our paper, we ended up with something new. When we burn our gas, we end up with something new. Right? When we burn the gas coming out of the stove, it reacts with the oxygen in the air to give us carbon dioxide and water. Right? And we're not really at the point where we fully know all of our chemical symbols yet, and that's totally fine. But if we think about it, right, if you've ever lit the gas burner without actually having the fire light, you've smelled the gas that comes out. When you're cooking and you have the burner on the right way and it's actually a fire going, you do not smell that gas because you are smelling unburnt propane when it comes out without the fire. And after, right, when it's burnt, you have carbon dioxide and water, neither of which carry a scent with them. Do all substances change when burnt? It depends how hot you make them, but everything... I want to be careful with that answer. But I am going to go with everything will react with oxygen if you get it hot enough. I'm going to stick to that answer because I can't think of anything that doesn't agree with that. What about salt dissolving in water or making a drink from powder? Right, is that a physical change or a chemical change? Just like the wet paper example from before, this is a physical change. When you have salt water or any other substance stuck into water, and we have our pile of salt mixed with our glass of water, we end up with salty water. We haven't made a new thing. The salt is still salty, the water is still wet, but now it's together in one place. We've made a mixture, and that mixture can be separated and undone, and so it's a physical change, right? We don't have a new substance from this thing. We just have two substances that are now occupying the same space. And then what about frying an egg, grilling a burger, cooking? Can all physical changes be undone? To an extent, yes. Right, the idea of cooking, the process of cooking, no matter what it is that you're cooking, unless maybe it's sushi, is a chemical change. Right, you are taking a substance and fundamentally changing it by cooking it. The exposition to the flames or the oven, right? However you're going to cook that substance, you're going to change it from one thing to a different thing. Right? A really good example of this is baking a cake. Right? You're going to take your flour, your eggs, your water, your milk, your chocolate chips, or whatever you're going to put in your cake. And you're going to combine those ingredients and then bake it. And when it comes out, it's no longer flour, water, eggs, and the rest, right? It's now a cake. It has become something different. Right? On the topic of chemical changes and the idea that you've made something new, we're going to talk just a little bit about chemical reactions. A chemical reaction, right, like the ones I was writing before, is shorthand for a full sentence. Right? And so we have these three sentences here that all say the same thing, but slowly morphing from written English to chemical formula, chemical reaction. Right? We use the symbols from the periodic table in order to write these reactions to show ratios of things combining, to show which version of carbon and oxygen is coming together. We use the periodic table just to get this shorthand version. But one of the really important things to note about chemical reactions and chemical changes overall is the idea that they only happen in the right conditions. And what that means is, going back to our example of a cake, you have flour, eggs, milk, water, chocolate, you put all those things together, stir them up, and if you just leave them on the countertop, they're never going to become a cake. Right? You need to put those ingredients mixed together in the right combination, right, the right ratios, into the oven to make it a cake. You need to get those conditions to the right spot. Right? The pen that I'm holding in my hand is made mostly of carbon. The air around me has a bunch of oxygen in it. My pen is not just going to become carbon dioxide like this formula says. Right? This reaction will only happen if we put those things into the right conditions. And with that, I'm going to end us for today and transition us over to our Google Meet. So come on over, we'll take attendance and go from there.